we're going to take a little bit of time to revisit inverse trig functions in calculus. And the reason we care about the inverse trig functions, particularly the inverse tangent, the others to a lesser degree, is because of the integrals they let us evaluate. In order to write down what the integral of 1 over 1 plus x squared, a pretty simple rational function, is, we need the inverse tangent. And the integral of an only slightly more complicated function turns out to be the inverse sine. While we're at it, we'll take a look at this integral, which really doesn't show up as often, but it is the inverse secant. And it would certainly be handy if, in addition to being able to evaluate integrals that looked like this, we could evaluate ones that had numbers other than 1 in these spots. And to come up with formulas that have numbers other than 1 in those spots in the integrals, we're going to look at taking derivatives of slight transformations of these inverse trig functions. So we'll put those over there just to not lose track of them, but give ourselves some more space here. So the first derivative of a transformation we're going to look at is the derivative of the inverse sine of u over a, where u is a function of x and a is a constant. So we just need the chain rule here. This will be equal to 1 over the square root of 1 minus the baby squared times the derivative of the baby. It's going to turn out to be useful to square the u over a. And this derivative of the baby, 1 over a is just a constant, and then we get times du dx. And notice that multiplying by 1 over a on the outside of the square root would be the same as multiplying by a squared inside the square root. And distributing. And now we've gone from having a 1 here to having something other than a 1. So that gives us a new, slightly more general antiderivative formula. If we have the integral of 1 over the square root of a squared minus u squared du, that'll be equal to the thing we started with up here. So with this result, we can evaluate an integral like 1 over the square root of 9 minus u squared du, where the pattern is the same as what we just found, with a squared being equal to 9, which means that a is 3. So this antiderivative is just equal to the arc sine of u over 3. Now let's look at a transformation of the arctangent that turns out to be useful. It's going to look similar but not identical to the transformation we used for arcsine. We're going to have still the inverse tangent of u over a, but we're also going to multiply that whole thing by 1 over a. And now let's take the derivative of this. So we've got a constant, and then the derivative of arctangent is 1 over 1 plus the baby squared times the derivative of the baby. One over a times du dx. Now we have an a here and an a here, which makes an a squared. So multiplying through makes our fraction a little nicer. And you can see we ended up exactly where we wanted, with the ability to deal with a number other than 1 in that rational expression when we take an antiderivative. So the new formula we'd like to remember here, this time it's not just the inverse tangent of u over a plus a c, but 1 over a times that inverse tangent. So for example, if we want to take the integral of 1 over 5 plus u squared, we can see that it looks like 1 over a squared plus u squared in the case where a squared is equal to 5. Therefore, a is the square root of 5. And so this will be the inverse tangent, just like with the sine, of u over square root of 5 plus a constant, and then we need the 1 over a. And we won't work through all the details for the case of the arcsecant, but it turns out that the transformation we want is exactly the same as the transformation for the arctangent. The integral of 1 over the absolute value of u times u squared minus a squared du is equal to 1 over a times the arcsecant of u over a. Whoops, I forgot my plus c up there and there. So here are our new formulas. And you should memorize those so that if you come across one of those expressions in the integrand, you'll know what the antiderivative is.